Welcome everyone to this third session on the RIOT Summit. This session will be about security. We have 4 more exciting talks for us, starting with Michael Richardson with universal key pairs in all devices. I hope Michael is already here. Anyway, yeah, Michael, I think most of us know Michael, but Michael is very active in the IETF, worked on mesh routing for IoT devices, into IoT security now. Thank you very much. Is also a RIOT maintainer these days. So Michael, if you're there, floor is yours.
Okay. All right. Hi. I hope you guys had a nice day, nice lunch. I'm Michael Richardson, and I guess I get the honor of being the first after lunch speaker, so you'll all be a bit dozy, I guess. And agreeable to everything I have to say. So that sounds good. So I'm Michael Richardson, and I guess I've been on probationary retainer for a little while, and I've been involved in RIOT OS for a few years now. So who am I? Well, I've been around for a long time. I call myself a garage entrepreneur. I've been involved in and out of many .coms, many of them involved with internet things, chips, firewalls, other things like that. And so over the years, I've been sucked into doing a lot of IETF work, and really it's quite enjoyable. It's what I like. And that's about it. Most recently, I'm involved in IoT onboarding, RFC 8995, Brewski it's called, and a bunch of other things. So what is it about here? The goal is that every device should have a strong identity. And what does this mean exactly? This is ideally about an IDevID. 802.11.1AR is a spec on device identity. Yeah, is that my...
That was the one. Continue.
Okay. Ideally, the private key is strongly implicated into the device. We're going to use that for all sorts of things, from remote attestation to MUD to potentially mutual TLS, and to find firmware updates, if not to authenticate them. And ideally, the IDevID also gives us some kind of strong device type and class, and therefore, if you know what it is, if you know what type it is, then you know maybe if, for instance, if the device is on the CRA compliance list or not. I realize at this point there isn't a list, but if you don't know what it is, then it's hard to know at all about whether it's in there. So call this a charting effort, a discussion, and I would love to audience to please interrupt, put your hand up. I guess somebody would have to do that. Let me know if there's someone that can't see the audience very well because they can't pick that view. I guess to speak up, interrupt, and go from there. So what is it about? The challenges, what are we? Well, basically, where are we going to put the private key? How are we going to preserve it across firmware updates? And where would we put the certificate when it exists? Because it doesn't have to always exist. The ideal thing, or doesn't always exist in the device. And who's going to do this? So other things, questions. So who's going to generate this key? Who will sign the certificate? And can we trust the device not to get its keys copied? Should we worry about hardware acceleration, or we don't care about key types such as ECSA, RSA, the various quantum safe things? Should we only do keys that have hardware acceleration, or should we do only things that are safe? And unfortunately, those two things may not overlap over time. And do we even carry device identities for a device that's never connected to the network, for instance? And the answer to me is a bit nebulous. So let's go through. So let's talk about some of the what my notion is. And I went through a couple different CPU architectures, and broadly, a lot of it's going to depend on CPU types rather than necessarily board types. But there's some back and forth. It's conceivable that some of the boards have secure elements, which are special chips that can, safely store or a private key without letting anything in and out. But it's a pretty expensive, power-hungry kind of thing to use in the space we're in. And of course, a TPM chip, which was separate, is kind of a high-end secure element. A secure element is maybe you can think of as a very stupid TPM. And the key part is that it can keep a secret and not tell. Some of the CPUs have trusted execution environments of various kinds, and some of them are usable and some of them are not. The key thing is that if you have a trusted execution environment, then in theory, you can have a firmware TPM or a firmware secure element, meaning it just runs in a secure execution environment and is therefore able to keep some things safe. Some of them don't, and some of them are hard to get into. So let's talk about one specific one I looked at. Was this, and I forgot the name of it, Kinesis, I think it was, chipset from NXP, and it claims to have some security. Go through the data sheet, the link's on the bottom there, and claims to have some security, 128-bit unique identifier per chip. So that's an interesting claim, and it can control whether you get access to read or write various flash and access control. And then it says there's no specifications necessary. And I was kind of like, well, there's a lot more you haven't told me yet. So where's the actual data sheet that tells me something useful? And I didn't find it. So it's unclear to me what you would do. So you could have a private key that is visible within the chip and not without. I suspect there's other details that are NDA details. And in theory, if you have that private key, then you can generate a certificate from it, and you can do it in a predictable, deterministic fashion. And therefore, the factory, if it's told the same key, can derive the same key, generate the same key, sign a certificate, and it works. That's one of 3 different ways of generating keys from the seed. But how would you know the seed? Where would it come from? Well, usually you get an Excel spreadsheet on a USB key, and it gives you the list of the 10,000 devices or something, or 100,000 devices that you purchased. So if you purchased 4 devices, the answer is you probably don't get anything. And that's means essentially there's nothing you can do because you didn't get it. It's a CPU without anything useful. So let's look at another example. The ESP32, the H series, which is the RISC-V. And the previous Extensa series has very similar things, if maybe some of the numbers are scaled down. So it has a secure boot. In theory, it has trusted execution environment available. Did not find a data sheet again that went deeply into that. If it's there, it might be there. Often their data sheets are a little bit buried. But it's a little bit unclear to me how you would start things off and how you'd use it and what kind of things you can put on it. And really, is it a trusted execution environment, or is it really just a ring 0? That is, the most privileged part of the CPU. It has this 4096-bit eFuse memory. So that's essentially a one-time programmable kind of flash. You can set 1 bits, I think, in it, but not 0 bits. Once that's set to a 1, you're done, and that's it. And there's space for 6 256-bit keys, and there's some other bits to obsolete them, and there's some bits to tell you what each key is for. Normally you put private keys there. You could also put trust anchors, and it's unclear how many of those keys can be used for one thing or the other, because there's a secure boot part which can use up to 3 of those keys for different kinds of that. So presumably a few else are left for trust anchors. There's not enough space for a certificate in there, but it's not really the right the right thing anyway. So we would still want to use something else for a certificate, even though we could, in theory, store the private key in the chip, and there's a little bit of secure access to it, so you can actually keep things from reading it and stealing it. It's unclear what the 128K of the ROM that's already in there exactly does. Presumably somewhere there's an SDK API manual that I found. And there's no built-in flash. So that means it's hard to make a memory map of the CPU because you don't know exactly how much flash there is. And that ROM does something about booting that things. And it could be, in fact, encrypted, and it could be decrypted if you like. So you could have actually encrypted firmware with the key in that eFuse. And it's unclear to me from what I was reading so far where our code runs. I imagine it all runs in the same security privilege, but are we abandoning the ring 0 TEE and running in one of the other 3 rings, I call them, the REE they call it, or what exactly? What do we need to do to still get access to the TEE to do something? And so that's an interesting question, because that gets us potentially a safe place to put the private key if we do it right. But if we don't, there's still a good answer, and that's what this is really what I'm interested in. So let's say we take this is our memory map, and we look through it, and we realize the flash goes up to a certain address, and we decide to take the last 2 erasable blanks as this variable, and in this case, let's say that it starts the bootloader starts at address 0 because that's where the reset vector is. And it picks the most relevant bank using, suit. So this could be MCU boot, it could be RIOT boot, a couple different things. And we just basically arrange such that we know that we're never going to overwrite those last 2 pages. We've told all the things for that. Fantastic. So there's RAM, there's peripherals, and now we just have to teach our PSA crypto that there's a key in there, and it should be able to find it. Variables, I'm going to talk about how to store them. So we could do it a different way for different CPUs. So in this case, another common pattern is the reset vectors at the very top of RAM or ROM. The flash is already there. We could put the MCU boot, the RIOT boot, put it at the top of flash, and immediately below it, we reserve 2 banks. We tell it, please don't overwrite that ever, and we have the double banked process. So again, negotiation about where exactly we're going to put this, and we have to come up with this essentially on a per CPU basis and potentially at a board basis, because if there's different amount of flashes, which there is on the ESP32, then we wouldn't know exactly where it ends. And the ESP32 doesn't look like this in terms of memory map, or like this. It's more complicated, of course. So what are we going to store in it? So I wrote a couple of years ago, and I haven't not finished and revised it again because they're distracted, but I'm coming back to this. I wrote this thing called CFG page, and it's a driver that basically maintains a map in memory. So if you've ever, seen what U-Boot has on OpenWRT or other platforms, there's a bunch of variables you can store in the system, and they persist across OS loads and boots. If you've ever hit L1A on a Spark station and then hit print environment, you've seen the same thing, exactly the same process for that. And it's interesting to think that some of our CPUs are probably at least as powerful as good old Sun 2s and 3s for sure. So what did I put in here? It's basically a CBOR sequence. It's got a few pieces at the top that identifies this piece as a legitimate initialized variable. And then the last item is a CBOR map. And it's an indefinite map, and it contains key values. And it just happens to be that the marker in CBOR for the end of an indefinite map is an all ones bit stream. And that happens to also be the same thing as what you get in most flash when you erase it. So an empty flash, in theory, has an empty map, which is kind of exactly what you want, especially when you erase it. So the keys can be repeated, which is a question in CBOR as to whether you allow that or not. And so we allow this to happen. which means that we can always append to the map, and we could create new values. As you see in this case, A had the value 10, B had the value 12. Then we decided to write A again with the value 11, and that's the current value. And then C is the string hello, and then the end of the map. And as you want to add things, you add things to the end of it. And when you run out of space, well, you garbage collect it and put it in the other map. So this is an example. You go through the map. I put there's a serial number in there. You increment the serial number from 1 to 2. You do that at the very last, just before you finish. And you basically copy things from bank, 0 to 1 when you ran out of space. And as you see, it copied the A is 11 and dropped the A was 10 old value. As you go through that, things that change to get have their last value done, and that's it. And I wrote a bit of code. It's a little bit complicated because it tries not to use any memory to do this, so it has to make multiple passes through the old bank, and that's probably okay because even though it's a O(n) squared algorithm, it only runs when you garbage collect, and it's probably cheaper than not. Probably during the boot process, you never update any variables, you never write anything, and only if you're going to have a successful boot, like for Suit or something like this, then you have to figure out how to put that somewhere else because you need a much smaller piece to write, or you need to do it by only setting ones. Only turning ones to zeros, which we can always do usually in Flash. So what other issues do we have? Well, so it's not enough because the values are repeated. It's not enough to just look and see how many bytes I have left to see, do I have enough space to write this thing at all? Might be that there would be more bytes available if you first do a garbage collection, but you might do that and then discover the item is still too big to fit. And so that's kind of a problem if you wind up there. If you have Flash where erasing doesn't turn to all ones, then you have to think about what to do. And there's some other assumptions there about that. You can always turn anything that has any number of bits set. You can always turn it to a 0 by setting more bits, and that's allowed even without an erase. So that's generally true for most Flash, but I'm sure someone has some Flash that works differently. That is just weird for being weird for that. Right now it uses our published MTD interface, which lives on top of NOR or NAND Flash, and as a result, and is assumed not to be directly addressable in RAM. So to work properly, it actually has to read and write bytes in and out of RAM, back and forth. There's a lot of calls. That makes it kind of a lot slower than maybe it needs to be, and I would prefer to just not support the NOR Flash at all. And have an interface that assumed NAND only and that it was memory mappable. That would be much easier simplification to the code, and we could discuss whether or not that's absolutely necessary or supportable everywhere. There are presumably boards and CPUs where it's all NOR Flash, which is SPI2 interface. It's copied to RAM, and that's it. And either they're not supportable, or the code that I wrote right now that supports NOR Flash would have to be used, and it would be it's more complicated and harder to maintain, but it's more general. Right now it uses the Nano CBOR library. We have a bunch of other CBOR libraries. I don't think we got convergence yet, and I don't think we will, like we have work for the CoAP work, but maybe. As I said, assumption that you can write zeros bits without erasing, and as a result, also the garbage collection is n squared. So how big do you want to make the store? Well, you have to make it at least big enough to put a certificate. So that might be a couple of kilobit bytes that you need, plus some other variables that you might want. So, somewhere between 4 and 8 kilobytes would be nice to multiply by 2 because you need 2 pages, and hopefully that fits anywhere. And then this comes back to, well, how big or small is the Flash erase page? And it varies by CPU, and because you may have NAND that's not in the CPU, it also may vary by a board. Many CPUs have, parts that are 128K erase pages, but then have a limited number of 8K or even smaller erase pages specifically for configurations. So you have to go through for each CPU. You have to make a plan, figure out what's going on, and figure out the rest of it. So questions like who creates a private key? Well, I'd love to take interruptions. I probably wasn't looking at the room properly at the moment. Well, ideally, I would love it if the board maker did it. They did it in their factory. They wrote a certificate for that. So I'm thinking, you know, Adafruit is an example. They're not a CPU maker. They make boards. But, you know, some of the boards are SDK boards that the maker has made. And we can put things in. And it's a back and forth. There's some conversation there to have. And initially, you know what? It's going to be us because we're the issues. We're the ones who want to use it first, and you know that's the story. So as I said, some things can protect it, some can't. The flasher could initialize it. It could have a RESTful interface to create a certificate. We can come back and forth of this in the conversation that I would like to have. Some boards can't protect that private key very well. It's just, you know, if you plug in a USB flash cable, you can read all of memory and you can therefore steal the private key. And the question is, you know, is good enough the enemy, is better the enemy of good enough? And is this good enough for our purposes for that kind of environment, different kinds of things? Some systems, of course, there's no problem. There's a USB adapter, but then we put it in a case and fill it with resin, for instance, so no one can plug it in again. And that's probably as good as many other things, since secure elements can be taken apart with a sufficiently well-funded entity. There's a lab on the other side of town from Ottawa that specifically does exactly that and does it in Canada because we're not subject to the DMCA. And, you know, it's not a question of can it be stolen? The question is how much do you have to invest to steal it? And so that's a sliding scale for that. So, you know, if you're going to create a product, you're going to create thousands of them, then you're going to do the signing, okay, of the certificate. But if not, if we're talking about, you know, a dozen, then we're up into layer 8, 9 issues as to doing what's going on. And we could do some things, and I'm very happy to be the stuckey for some of that if we want to go forward for that. And that's really the slide. That's the discussion. Is this good enough? Is this a path that we can get onto? And I think it kind of involves fairly cross the project, or at least cross device project thinking and discussion. And yeah, some of the boards some of the CPUs we support are maybe so old and slow that we would just say, no, not going to bother. They have effectively no network interfaces that we could ever use. So forget it. And other ones like, say, the ESP, well, they're pretty far along the way, and we just have to figure out what our plan is, and we have to document it. And ideally, we're going to talk to, say, Zephyr and some of the other embedded operating system peoples and try to convince them that our plan is a good plan, and they should adopt it too. Questions? I probably went over time.
Thank you, Michael. I think we have time for 1 or 2 questions. No questions? Yeah.
Would we get? Are you doing Unix CBOR then, as you wrote?
So the thing, question is, does it make sense to have this across all boards like in a single format, or might it make sense to have more like an information model that we can then apply to whatever exists in the ecosystem? Because, for example, looking at what's it called, language as smartphones, for example, that has a like per board known configuration area already.
Right.
Would it make sense to have an information model that we then map onto whatever is available in that board and just fall back to the 2 pages of SQL Flash where nothing like that exists?
So I remember reading one absolute data sheet where there was a very clear configuration area, but it was just some Flash pages that were smaller that you could erase more easily. They didn't tell you what to put in there. I don't remember one that actually had it's small enough to store like individual variables easily and erase them. But if it does exist, great. And in some cases, there's a place like in the ESP, there's a place to put a private key, a 32 bytes of fuse one-time writable private key. And there's ways to protect that. And that's great. So put the private key there. And as you said, PSA can say, oh, there's a slot interface. I can go from 0 to 5, I guess it is. And that'll work fine. But 32 bytes is not enough space for the corresponding IDevID certificate that has a bunch of other extensions and useful things, for instance, a MUD reference, other things like this. So you still need to put that somewhere. So it's a better story. And the reason why I think this needs to be standardized at a byte level and not at an API level is that what we would like is we'd like the various flashing tools, whatever they are, ESP tool, there's other ones for each one has its kind of own tool. We would like to teach that, first of all, to avoid those pages, obviously, but secondly, to notice if the pages are in fact completely uninitialized, in which case it should initialize it, and that only happens once really, and it might be that it needs to have the key pair generated and enrolled and installed at that point. So you would run the tool, you would run it on a whole bunch of things. And, the ideal would be is that we have board vendors that are doing that operation and, and not filling the rest of Flash at all, and then done. Or, maybe they install their default Arduino or some other easy to Flash, OS that boots, or to use it to flash your own thing into it. And that's great, but they're going to initialize the whole thing. And so when we get them, they would have a key pair already there. Fantastic. And then we would, write RIOT OS over whatever Arduino.
Thank you, Michael. We're out of time for this slot.